slides, you would find my details. Like you already know, my name is Linus Antonio Oforie-Jekum, and you have my number as well there and my official email. Now, the course is a 3-credit-hour course, which means that every week we're supposed to meet for 3 hours. But per your timetable, I think it was only 2 hours that was made available. So we agreed to Tuesday 11 to 1, but unfortunately we haven't been able to meet. So the course assessment structure for the semester, what is going to happen is that a lot of the things we are going to be doing, I think we'll do everything virtually. It's going to be online. Instances where you feel there is the need for some tutorial, we can have a face-to-face meeting and do that tutorial, or we can still do the tutorials online. Now, class attendance, which is your presence online for any of these sessions, is considered compulsory. So you would have to be in class for all the sessions, be it face-to-face or virtual. Then I may give you guys assignments as time goes on, and these assignments would contribute 15% to your continuous assessment. The class attendance, that is, if you attend all my classes, you would get automatic 5%. However, if you do not attend all the classes, we would look at the number of classes you attended and the number of classes we've had, and that percentage will determine how much you get out of the 5. In 2 weeks' time, there's going to be mid-semester exams. I think in 2 or 3 weeks' time, there's going to be mid-semester exams. And that is also 20%. And then as usual, we'll write an end of semester exams, which is going to be 60%. So that is how the exams is going to be. Just 1 second. Now, since we are online, let's not worry ourselves with these policies or class policies. Now, let's look at the objectives of this course. If we are going to take digital signal processing, what are some of the things we would want to understand or we need to know after we have completed this course? Number 1 is to understand signal sampling, reconstruction, and aliasing prevention to ensure faithful digitization. So when we talk about digital signal processing, it's basically using a digital system to process a signal. It could be that you are amplifying the signal strength. It could be that you are filtering the signal. It could be that you are encoding the signal or you are decoding the signal. So we would need to understand something we call sampling, as well as how to reconstruct signals. And then aliasing is a term we use when in the process of sampling, you sample less than a certain frequency, then you would have a phenomenon occurring which is called aliasing, which can lead to losing of some part of the signal. The second objective is that we would want to analyze digital systems for linearity, time invariance, causality, and stability. So if we take signals, for instance, we'll look at them in terms of these properties, whether it's a linear signal, it's a time invariant signal, or it's a signal with some stability. Then from there, we would also need to understand or master convolution techniques. that is using graph, table, or matrix to help us distinguish between linear and circular convolutions. So these are the objectives at the end of the semester. These are the things we expect to know or to understand. Now, let's go into the course structure or the course outline. So we have some modules. I decided to put them into modules instead of in units, but the slides I share with you, you would mostly find them as units. So the first thing we are going to be doing is Introduction to Digital Signal Processing. We'll try to understand continuous or analog signals and also try to understand the limitations there are with analog signals. And then we'll see why there is the need for digital signal processing. And then we'll move on to signal sampling and reconstruction, where if a signal is transmitted and the signal at the receiver is an analog signal, how do we convert it into a digital signal? Or how do we reconstruct signals? We'll look at that in topic 2. Then in topic 3, we'll look at digital signals and systems. So here we're going to be looking at these signals and we'll look at their classifications in terms of linear systems, time invariant systems, causal systems, and then stability. And in our 4th topic, we'll look at digital convolution, which I earlier on mentioned as an objective. Then we'll go ahead to look at frequency response and sinusoidal steady state response. Then from there, we'll look at Z transforms. We'll review Z transforms. Then we'll look at discrete Fourier transform and then fast Fourier transform. So we're going to look at DFT and then FFT. Then we'll look at some algorithms in fast Fourier transforms. Then we'll look at analog filter design. So we'll look at the Butterworth filters, the Chebyshev filters, etc. Now, do you guys know how to use MATLAB? Is there any one of you here who has ever had an experience with the usage of MATLAB?
No, sir.
None of you?
Yes, sir.
Hello?
Hello, sir.
Okay. So I am teaching a similar course this semester, and most of the things we do are on YouTube. So I'll share some of the links with you. And then when you get the time, pass by my office and then collect the software and install it on your laptops. When we get to some of the examples, I would give you some MATLAB exercises to do. For instance, designing of filters, that is Butterworth filters and then Chebyshev filters. And you would be given some signal to process, a signal with noise. And you'll be asked to process and take out the noise so that you can have a feel of how this is done using MATLAB, okay?
Okay, sir.
So with digital filter design, we'll look at infinite impulse response, that is IR filter. Then we'll look at the FIR, that is finite impulse response filters. Then we'll finally look at the realization of digital filters. So these are the things we are going to be covering this semester. Now, as mechanical students, I am sure in your mind, you would be asking yourselves, so what do we need signal processing for? Is that not the case? Or you already know why you need to study signal processing?
No, sir, we don't know.
Okay. So in your line of work or in your field, which happens to be dealing with systems, in some cases, automotives, in some cases, engines, a lot of the systems or mechanical systems today would have some control units, which would normally help to control the mechanical moving parts of the systems. Now, all these are electronics, or they are electronically operated. Most of them operate with signals, and these signals would have to be processed. So now the systems that are used to process the signals to allow for controls are what we call these digital signal processing systems or digital signal processors. So it is very important that as a mechanical engineer, you understand what DSPs are and how they operate, because you would not only maintain systems, but you would also design systems as and when the need arises. Sorry about that. So like I said, you would need to understand how DSPs operate or signals operate, because as mechanical engineers graduating with bachelors, you are not only just going to be maintaining systems. There are instances where you have to design systems as well. So you would need proper understanding of these things to enable you do proper troubleshooting or designing of mechanical systems. Now, as we go through this course, there are some reference materials that you can read. I would give you slides every now and then. The slides most of the time will be very self-explanatory, but in order to expand your understanding or to get broader understanding of the course, these two textbooks are reference books. The first one is John Proakis and Dimitris Manolakis, Digital Signal Processing Principles, Algorithms, and Applications. Third edition. Whatever edition you get to read, that is fine. That is acceptable. It will give you the same fundamentals. Then there is Applied Digital Signal Processing Theory and Practice, which is also by one of the same authors of the previous one, which you can find online to download and then make them your reference materials. So, gentlemen, this is basically a brief about the course. Any questions? If you have a question, just feel free and raise your hand. I would mention your name and you can go ahead and ask your question. Godwin, do you have any question? Someone should tell Godwin that I know he's on a call, so he's not paying attention to what I'm teaching. So it's either he leaves the class or he continues with his call. I'm going to continue with his call or join the class. Alfred, any question? Dennis.
No questions, sir.
Aziz. Aziz. Aziz, any question?
So I think none of them have any questions, and I think some of them have muted their
Yes,
microphone.
I want to hear them speak, because as I speak, they are listening. It means they've
Okay.
logged on there and they are sitting somewhere or doing something else.
Okay, sir.
Elijah, any question? Who joined with the link?
So I joined with the link.
I also did the link.
I also
No, I mean someone is joining through a web browser. Anyway, okay, all right. Yes, Alfred, your question. Unmute yourself and talk. I have allowed your microphone, so unmute yourself.
So I believe the network was bad, so I couldn't hear the latter part of what you said.
Where did we get to when your network got bad?
It was breaking. Since you were telling us about the reference, the book that we should read, yes. And
okay, so on the screen, you would see two books that I have shown on the screen. And these are reference books. I would give you slides as we continue. And then these books are just there for you to reference. So when you need to get broader understanding on any of the topics I may have covered or I would cover, then you can go ahead and read these books. They are very easy to find online in PDF forms. Okay?
Okay, sir, thank you.
All right. And then most of the time, I would record our lectures so that you can get back to them if you have forgotten anything or if you need to reference any other thing. So take note of that.
Okay, sir. Thank you.
Okay.
All right. So this is basically just to tell you about what we are going to be doing. Let's quickly look at Unit 1. Okay. So Unit 1, we're going to be looking at, that is Introduction to Digital Signal Processing. Okay, for Unit 1. The first thing we would want to look at is signal and flow of information. When we talk about a signal, what is a signal? A signal is basically any physical quantity A physical is basically any physical quantity that varies with time, space, or any other independent variable. So for example, if we're able to measure any quantity that varies with time or position, that can be termed as a signal. Now, we have signals in electrical form. For example, an electrical signal received from a transducer. When we talk about a transducer is basically a device that converts one form of energy into another form, or a certain state of energy into another form. So a microphone is a transducer, okay? A thermometer, for example, is a transducer. An accelerometer is a transducer. An antenna can also be classified as a transducer. Now, let's also look at an example in terms of an electrical signal that controls a process. So let's take, for instance, in a manufacturing plant where, let's say, bottles are filled with fluid. Let's take, for instance, let's use Twillium, for instance, as an example, where they have a plant which allows them to be able to fill water, bottles with water and cap them. Now, there would normally be some switches, or there will be a panel that is used to send signals to the various parts of the plant. Now, these are also examples of signals that we are talking about, okay? Now, a signal, like we said, can be represented with time or in terms of variables. So when you look at S1 of t equals to 5, or S1 of t equals to 5t squared, this is an example of a signal, except that this signal has only one variable. So the only thing that changes in that signal is t, or time. Now, when you take S of x comma y, which is equals to 3x plus 4xy plus 6x squared, you will see that this signal has two variables, that is x and y. So at every point in time, depending on x and y, we would have a certain value for the signal, okay? So this is just a representation of what a signal looks like. Now let's look at continuous time signals or analog signals. An analog signal is defined for every value of time, and they take on values in their continuous intervals as shown in the figure. Okay, so when you look at this signal here, continually, with the waveform you see, at every point in time, we would get a value for f of t. Okay, so continuous signals are continuous in time. Their amplitude may take on any value in the continuous range, that is from negative infinity to infinity. So here, you would see that when you look at the signal, that is, you have the x and y axis, you have the x-axis where you have time, which is t, and then for every time, you have a corresponding what? Frequency or function of t. Now here, what you would see is that the signal will have amplitude from the negative side all the way to the positive side. At every point in time, there is an amplitude value, okay? Now, analog signals or continuous signals would need to be processed with an analog processor, okay? And some of the basic processing that analog signals go through is differentiation, integration, filtering, amplification, or the processing of what? Differential equations. And all these can be implemented by the use of passive or active electronic circuitry. Now, when we talk about passive or active electronic circuitry, yes, Alfred, your hand is up.
Yes, please. Please, you said for analog signal is from this particular one is from negative to positive. So is it always from negative to positive, or we can also get from positive to negative?
It can also start from positive to negative. You would normally not get from positive to negative. It would either come from the negative to positive or from the origin.
Okay.
Do you understand?
Yes, sir.
You would never have a signal ranging from positive to negative. That would mean it's in the backward plane. Unless it is a mirrored signal, then probably the signal has a certain origin and then it is being mirrored from the positive plane to the negative plane.
Okay, sir.
All right. Now back to my question. My question is, when we talk about passive and active electronic circuit.
Maybe like battery, because it produces current. And then passive, I would say wire, because on its own, it doesn't produce any electricity, but it allows it to pass through. Is this one also part, or what I'm saying is wrong?
Are you asking or you are telling us? That is your idea.
Yes, sir.
Any other person? Now, with basic English, when we say something is passive, what does it mean?
It's neither active or inactive. So it's in the middle.
You are just playing with semantics. Yes, any other idea? Anyone else to help us? Yes, I'm waiting. If you guys don't explain this thing, we'll move on. This is something you should know.
Oh, sir.
Yes, sir.
Please, I think the passive ones are the components that don't amplify or control signals.
They don't do what?
They don't control signals, right? They don't amplify them, like the resistors, the capacitors, and those things.
They are what?
They are the passive components.
Okay. And then the active ones?
And the active ones are the ones responsible for amplifying or controlling the signals.
There is something I'm looking for. You are there, but there is something I'm looking for. Any other person?
Yeah, so passive electronic circuitry don't allow for external power. Wait. I think it does not allow for, it does not require or does not need external power source to work.
And then the active.
The active itself is the power source, is the external power source.
So basically, circuits that do not require power or do not require any source to be able to operate are what we term as passive circuitry. And then for active circuitry, they are circuits that would require power, constant power to be able, or constant source to be able to perform whatever function they need to perform. So as an exercise for you, go and read on passive and active components and try to understand what active components are and what passive components are, okay? So what we are basically saying is that for analog processing circuits, we do that using active and passive electronic circuits, okay? All right. Now, let's look at digital signals. A digital signal is a signal that takes on values from a finite set of possible values. So the signal you see here is a signal with 4 different amplitude values. So you would realize that some of the signal amplitude you see, for instance, at n equals to -1, 0, 2, and 6 have the same amplitude. 1, 4, and 8 also have the same amplitude. 3 and 7 have the same amplitude, and then 5 also has 1 amplitude, okay? So for digital signals, instead of having amplitudes continuously over time, for discrete or digital signals, you would have discrete amplitudes, okay? They are discrete in amplitude and discrete in time, meaning they are very particular, or they are specific at a point in time and then at a point in value or magnitude, okay? This can be obtained from discrete signals via quantization. There is a process of converting signals to digital signals, where when you have a continuous signal, like an analog signal, you convert the analog signal into a discrete signal by sampling. So you sample certain points on the analog signal to have as many points you would get on the analog or continuous signal, so that you can retain some of the information or the vital information that is contained within the signal. Then after sampling, that is where, when the sampling is not properly done according to a theory we would look at, we would have something we call aliasing or aliasing, okay? Now, after that sampling has been done, we do something we call quantization. Now, that quantization is what maps the various amplitudes of the discrete signals to a certain amplitude or a certain level before they are converted to what? Digital signals using some digital techniques. So this is how we represent digital signals, or a representation of a digital signal, okay? Any question? Any questions so far? If there is no question, let's move on. Let's look at finite and infinite length signals. When we talk about finite length signals, these are signals which are non-zero over a finite interval. That is when we have time minimum and then time maximum, as we can see in the diagram, okay? The length is non-zero, whereas in infinite length, the signal is non-zero all over the real numbers. So this is basically a representation of a finite signal, as you can see in the image. Okay. When we start working with the systems, we'll do a lot of these representations with real values, and then you would appreciate how these signals are processed. What is signal processing? What is signal processing? Have you ever had an instance where you probably visited or you were in an auditorium, and then whilst the person who is speaking, the lights go off or the microphone goes off, and then the person who is speaking and you cannot hear? Have you had that instance before? Or have you had such an experience?
Yes, sir.
Yes. So the microphone that the person is using has some form of a digital signal processing or a signal processing feature that allows the signal from the person's mouth, which is the speech, to be processed and amplified. Okay. So signals can be transformed in order to, number one, amplify or filter out embedded information, detect patterns, prepare the signal to survive a transmission channel. So when we talk about a transmission channel is basically the medium in which a signal will travel from one destination to another destination. So let's take, for instance, if you take the mobile towers, you have one tower at location A and then another tower at location B. The medium with which the signal travels, that is the microwave signal, through the free space, that medium is what we call the channel. And most of the time, in order to have signals go through channels, they would have to take on the feature of the channel before they can survive transmission. So we process signals to also help us prepare the signals so that they can survive situations like transmission. Signals can also be processed or transformed to eliminate distortions contributed by transmission channel. Now, let's take, for instance, as I am recording this lecture, there is some noise coming from outside, just like I experienced recently or a while ago. It will so happen that after saving whatever recording I have done, there would be unwanted signals. And these unwanted signals are signals that did not come from me, but probably came from my environment. So in processing such a signal, we'll take out the distortion, the noise from it. So that is also a way of processing signals. In some instances, when you transmit signals from one location to another, there could be losses. In some cases, between sensors, there could be some losses. So in order to compensate for these losses or deficiencies, we would also do what? Signal processing. In some cases, we do signal processing to find information encoded in a different domain. Now, we can process signals in time domain, and we can also process signals in the frequency domain. Okay, so when you look at the image or the diagram illustrated there, signal processor, be it analog or digital, will contain some unwanted signal, for instance, or would be able to process a signal which contains the useful signal, some noise, and some unwanted interference. So when it goes through the signal processor, it is able to take away the unwanted interference and also the noise, so that we have an output that is fit for purpose. So this is basically a brief explanation of what we mean by signal processing. What this means is that we can process signals using analog signal processors. We can also process signals using what? Digital signal processors. Please, do we understand?
Yes, sir.
Okay.
Yes, sir.
Now let's make progress and look at this system here, which is an analog signal processing system. So let's take, for instance, we have an analog signal processor as shown in figure 6, which is a typical analog signal processing system with some analog input. Now the analog input could be in terms of time, it could be in terms of space, and then it could also be in terms of frequency. So x of t would normally give us an output which is equals to y of t, which is equals to h of t times x of t. Now, h of t here is basically a property of the signal processor. Okay, so where h of t is the system impulse response, and then h of s is the system transfer function, and then h of omega is the system frequency response. So in this case, this analog signal can process in terms of transfer function, in terms of impulse, and then in terms of what? Frequency. Like we said earlier on, analog signal processing is achieved by using analog components. Now, these components comprises but are not limited to resistors, capacitors, and inductors. These are components that are used for analog signal processing. Now, let's look at some limitations of analog signal processing. The first one is accuracy limitation due to component tolerance and desired and undesired nonlinearities. Now, these components are designed to have some level of tolerance, and these tolerances can contribute to accuracy limitations, or they can reduce the accuracy of signals. They can also lead to limited reliability, and these can also be contributed or can come about because of tolerance, environmental conditions, temperature, and also vibrations within these components. That is, when the components start heating, they also affect reliability. Okay. Now, sensitivity to electrical noise. These components are able to pick up electrical noise so easily. And because of that, they do not affect or they do not help in processing signals properly. Now, because of the dynamic range of voltage and current in systems, we would also have analog processing have some deficiencies. Because they are analog signal processors, they do not have, or they have inflexibility in changes. So this is also a limitation. Now, operations like nonlinear operations or varying operations are very difficult to perform or to implement. And then finally, it is very difficult to store analog signals. Their storage is difficult, and it also occupies a lot of space. These are some of the limitations for which we would want to do digital signal processing. Because analog processing does not give us an easy way to store information. They lead to difficulty in implementing certain operations like nonlinear and varying operations. Because of the dynamic range of voltages, analog processing is also very difficult. Because of the sensitivity or the components in analog systems or analog processing systems being sensitive to electrical noise, they also limit the efficiency of the processor. Okay, so these are basically some limitations of processing with analog signal processors. Digital signal processing, however, is one of the most powerful means of processing signals, especially in our world today. And because of that, we are able to process signals in the field of communication when it comes to sensors as well as radar. So today, for instance, sensors, you have smartwatches that have sensors that can detect your heart rate just by picking analog information from your pulse. And then the sensors are able to process that analog signal and give you a digital output on your phone. Today, when you go to the hospital and you look at the various equipment that they use in monitoring, for instance, the BP apparatus, you see that we've gone past the stage where they used to use that analog one where they will pump and then it'll fill a certain tube. And then when they release, that is when they are able to tell that your BP, the systolic and the diastolic is so and so. Now, all you need is just to put the sensor around your arm and then you turn it on. The sensor picks the pulse, and then because of a digital signal processor, it is being converted to what? A digital signal, and then you can see the reading on the screen. DSPs convert signals that are naturally accrue in analog form, such as sound, video, and information from sensors. So for instance, with the example I was giving, the signals we pick from our pulse, they are analog. But because of the help of transducers or sensors, the sensors are able to pick these pulse, convert them to electrical pulse, And then by the help of something we call analog to digital converters, these are converted to digital signals before they are processed by the DSP. Okay. So when you look at the illustration here, the diagram you see in here, you would see that this is a typical digital signal processing system where you have an analog input. In this case, let's take, for instance, that analog input is a voice signal, a speech. There is an analog filter which is supposed to filter out some unwanted analog signal, and this becomes a band limited signal. Now, the band limited signal, what it means is that after the filtering, we have taken only the portions of the signal that is necessary for usage. But we would need to convert it from analog to digital so that it can be processed by a digital signal processor. So we have something we call the ADC. That is the analog to digital converter. What the analog to digital converter does basically is that it converts the analog signal into a digital signal. And that is the input that goes into the DSP, which is the digital signal processor. Once the processing is done and it needs to be given out in an analog form, then we would need something we call the digital to analog converter. And this would convert the signal back from from a digital form into an analog form. So a typical example like I gave in the voice signal, which needs to be processed for a large crowd to be able to hear the voice and hear it in a soothing sound. Once this is done, the processing is done, it is then converted back to an analog form and then fed into a speaker. But in this case, a reconstruction filter is used to take away if there is any problem. The reconstruction filter would take just the wanted signal and then the output would be given in the form of an analog output. So if it is voice signal that is being fed to the system, the output will now become what? A sound for the audience to hear. Now, why do we use DSPs? Or what is the reason for DSP systems? Rapid advances in integrated circuit design and manufacture are producing more powerful DSP systems on a single chip at decreasing size and cost. Now, there is a technology we call the VLSI or the LSI technology or the silicon on chip technology, which allows that circuits which, if they were analog, would have been very big circuits, are now being produced to become very small circuits or chips, which in turn reduces the size and also reduces the cost. So there will be no need to go using an analog processor, which comes with a lot of limitations, when you can get a single chip, which is also cheaper. Now, digital signal processing is inherently stable and reliable. When we looked at the limitations of the analog signal processors, we said they had some limitations because of electrical noise. Digital processors do not have that limitation. They are not affected by that. So that increases their stability and reliability. Good processing techniques are available for digital signals, such as data compression techniques, error correction for channel coding, and then equalization, and then security processing techniques. That makes digital processing better than analog processing. So these are basically some, but not limited to this, reasons for using DSPs. They are easy to mix signals and data using digital techniques known as time division multiplexing. So in an instance where I have several signals that needs to be transmitted over a certain channel, I can put all these signals together and transmit them, but I would put them on different time slots. So that is one other advantage of DSP systems. It is easy to change, correct, or update applications, such as that needed in implementing adaptive circuits. Sensitivity to electrical noise is minimal, like I explained earlier on. And then digital information can be encrypted for security. And it can also be easily stored. So these are some of the reasons why we would use DSP systems. Now let's look at some applications or some areas where DSP is applied. Digital audio and speech. I think I earlier on gave that as an example, which I explained. We also have the digital telephony, where today we are able to use smartphones. We're able to make calls or place calls across continents. In the automobile industry, because of DSPs, a lot of cars are able to do so many things. Cars have features that are able to control the vehicle in different ways. We have automatic cars today because of DSPs. We have autonomous vehicles or vehicles that are able to drive themselves because of digital signal processing systems. In the electronics communication industry, they are also used. In the medical imaging equipments, so for instance, you go to the the hospital, and then someone has a baby, a woman has a baby in their belly. And they want to take a scan and see how old the baby is. Just by that probe with some gel, the probe is able to pick up the pulse within the uterus, and then it's able to give us an image of what is happening within the uterus. And with the help of DSP, you could measure the length, you could measure so many things. With that, today we are able to take MRIs. There are CT scans. In the multimedia industry today, we have all kinds of ways of having media just because of what? DSP. In the military, however, this is also used in communication. and as well as in the mechanical industry. So these are areas where DSPs are useful or they are used. So this brings us to the end of basically Unit 1.